All right. So we're going to start looking at polynomials and how we could write equations for a polynomial given some information. Like, we're not going to have everything, but we're going to have some information. And the fundamental theorem of algebra, super complicated name for if I have a polynomial, I can find a root for sure. It might be imaginary, it might be real, but I can get at least one root for any polynomial. That's what that's saying. I can find a solution. It might be real, it might be imaginary, but I can find a solution, at least one. Usually more than one. With our complex factorization is what this is called, I can write a polynomial using those real or imaginary roots into a factored form where all of these, they're just saying C1 being a complex number. It might be real, it might be imaginary, but I could write it in a factored form, x minus that root. And I can use that even if our root is imaginary. And when we have a polynomial that has a degree of n, we're only going to be working with positive polynomials because then we're not polynomials, our degree is negative. But if our degree is n, I can have at most n roots. I might have exactly n. I might have a couple less because we might have a double root. That's when we're going to have less. But I will have at most n roots. I cannot have more than that. So if I have a degree 3, I will have at most 3 roots. I might have 2, I might have 1, but I have to have at least 3. Or I will have up to 3. That's what I was trying to say. There we go. We'll have at most 3. There were the words that were being stuck in my brain somewhere. It happens every now and then. So what's going to happen and how we're going to see these problems given to us first is we're going to be given a list of zeros or list of roots for us to use. Erase this for a second. And a lot of times we'll be given a degree. So we're going to spend time writing polynomials like this. There's going to be times when we're going to multiply them out. Very rarely are we going to multiply it out fully into standard form, occasionally, but we will have pieces that we have to multiply out. I'm going to say again, you don't necessarily have to write down every word. If you want it, totally fine, and I'll give it to you. So what we're going to be working with for the most part is stuff we've done. The only thing that's going to be different is when we have imaginary roots that we're writing into something like a factored form. And we're going to see what that looks like here in just a second. Because we're going to have one other word that we see frequently that we might have heard, we might not have heard. So on our next page, I have 3 problems for us and a definition. But surprisingly enough, they all fit very nicely on one page. And they're not tiny. What's up?
If you're doing like a synthetic division and you get into like your root that you use a fraction, are you able to just do it on?
Yep. We did one kind of like that yesterday with the 1/2. I'm going to show you just because I'm going to not change the bigger right on it. 7.5, so like 1/2 fraction, just those drops. Ready?
No.
Okay, look at in a minute. I'm going to change it. Remember, I always post a PDF, but again, we're going to work through these, I promise. So, we're going to also work with something called multiplicity. We may or may not have heard that word before. Multiplicity is when a single factor, which we've written as x minus c here, happens more than once, like a double root, could be a triple root. That fact that it happens twice would make it have a multiplicity of 2. If it happens 3 times, it has a multiplicity of 3. It just means there is a power on that one specific factor. So if a factor occurs multiple times in a polynomial, in its factored form, that number of times it happens is the multiplicity. So we're going to be given problems like these down here, where we have zeros that we're given. So for A, we're given zeros of 2, 4, and negative 1. And we know this polynomial is going to have a degree of 3. So if we want to write a factored form of a polynomial that has zeros at 2, 4, and negative 1, what would that look like in factored form? X minus 2, x minus 4, and x minus negative 1, which becomes x plus 1. Change colors too soon. If we know our a value, we would be able to put that here. We don't know it. There is an a value. We just don't know what it is. This has a degree of 1, 2, 3. So this would be a polynomial in factored form that has roots at 2, 4, and negative 1.
Could you slow down, please?
Yep. This first kind of one, like A, you've done before in Algebra 2. We're not going to be working on finding A here. We're just writing it like that. That is the entirety of question A here. Degree 3, the only place that's showing up is we have 1, 2, 3 x's being multiplied together. So if we were to multiply this out, we would have an exponent of 3. We're just leaving them in factored form. So the degree a lot of times is going to be a way for us to check. I'm going to keep trying to drink from the empty coffee cup. Okay, let's take a look at B. Very, very similar. We just have a little bit of extra information because now I have zeros at 3 and 1 that each have a multiplicity of 1, which just means it happens one time. So that's like a normal factor. So if we write our, I'm just going to call this one g of x for reason because it's like a different equation. You can also just keep calling them f of x, totally fine. It's going to have an a value of some kind. We just don't know what it is. So I'm just going to put an a and call it good. For my zeros that have a multiplicity of 1, it is just like these zeros up here. It is x minus whatever our 0 is, whatever our root is. So we're going to have our x minus 3 as a factor, and our x minus 1 as a factor. What the multiplicity of 1 means is that it just happens once, or it has a power of 1, which we don't typically write. Multiplicity of 1 is kind of the default state. When we have something that says a multiplicity of 2, like our root at 0, we can start this out, writing it out exactly the same way. X minus our root, x minus 0. You do not have to put the x minus 0 part. If you can do just the x part in your head and have it be there, awesome. For some of us, it's going to help to put the minus 0, which is totally cool. But it's got a multiplicity of 2, so it means it's going to happen twice in this function. So it's squared. Or you can write it again and put x minus 0 times x minus 0. You could also just write that as x squared, because x minus 0 is just x. Just trying to, I like to follow the same kind of formula here, so I try not to change my approach too much through it. So you could also write this as our g of x a, x minus 3, x minus 1, x squared. That would also count. Totally valid, 100%, even in the same order. Scooching it off the wall. Either way is fine. There we go. Just trying to make up the flow. We can even do this with imaginary numbers. So on this next one, we've got a couple of different pieces. I've got a root at 2 with a multiplicity of 1. I've got a root at 1 with a multiplicity of 2. And then we have 3i. Ew. One thing that happens with imaginary roots, and the book expects you to kind of know this or almost figure it out sometimes. Imaginary roots always, 100% of the time, come in pairs. Every single time. Imaginary roots always come in twos. They always come in pairs. So if one of our roots is 3i, we are also going to have a root at negative 3i. Every single time. Imaginary roots come in pairs. So even if it just says I, it is plus or minus I. If it says 2 plus I, it's going to be 2 plus or minus I. We always have imaginary numbers in pairs. So when we write this into our kind of factored form, I'm just going to call this one y this time. Still going to have our a out in front that we don't know. I'm going to start from over here. So I'm going to have my root at 2. So putting that as a factor, we're going to have our x minus 2. We're going to have our 1 as a 0 with a multiplicity of 2. So we're writing it as our factor. X minus that 0, x minus that root, x minus 1. But when we have that multiplicity of 2, means we need to square it. So multiplicity of 2 means it gets a power. When we're looking at these imaginary numbers, we're going to write these out. We're going to have our x with the positive or plus 3i, so x minus negative 3i, and x minus 3i. We are always going to have pairs when it comes to imaginary numbers, every single time. I put a plus or minus on the 3i. And then I have x minus negative 3i and x minus 3i. Yes, dear. Yeah, I'm right fast. When we are writing out these equations, because right now we do have degree 5. 1, 2, 3, 4, 5. We don't leave i's. So we are going to have to multiply this out a little bit. We are not going to multiply fully out to standard form. But we do need to multiply the imaginary numbers together because we don't get factored forms like that. So we're going to multiply just those two pink ones together. Not the whole thing, just the ones that have i's in them. So if we just multiply these two together, we're going to have our x squared plus 3xi minus 3xi minus 3i times 3i, 9i squared. What do we notice there? The middle terms cancel out. And the fact that we have I squared means negative 1. X squared plus 9. So this whole equation written in its factored form we would write this as our y equals a x minus 2 x minus 1 squared times x squared plus 9. When we're writing it as a factored form polynomial, we don't want any complex numbers still in it. So that would be how we'd write our equation. Questions on those three? I know it's a bunch. Okay. Ready? So, our next problem, we're going to have trying to write an equation for a polynomial in standard form. So now we are going to multiply it out, and we need to have our a value. Whole kit caboodle. We're given some zeros, and we're given a condition. We're given a point. So we're told we have zeros at 4, 1, and negative 3, and that f of 6 equals 180. I'm going to give you guys a second to write that all down. So we're going to start out 100% exactly the way we did before, where I'm writing my equation, my f of x, using the zeros we have. We don't have an a value. We're going to have to find one, but we don't have one right now. How do I put these zeros in as factors? Mm-hmm. X minus negative 3, which is the same thing as x plus 3. So we're starting out exactly the same way. That is our generic kind of factored form for any polynomial that goes through those three roots. What can I do to try and figure out what a is going to be if I know this information? Mm-hmm. Yeah. This is saying that when x equals 6, f of x equals 180. So I have an x, I have a y, we can solve for a. I'm going to substitute in the 6 for x, and the 180 is our y. So we're going to have our 180 equals our a times 6 minus 4, 6 minus 1, and 6 plus 3. Substituting that 6 in place of our x. Where can I go from here? Yes. Yeah, you're just about a couple steps on me, but yes, you're there. Because we're going to take this and we're going to simplify. We've got our a times 6 minus 4, which is 2. 6 minus 1, which is 5. And 6 plus 3, which is 9. When we substitute that x in, it makes it so that I can simplify these down to just single numbers. Then we have 2 times 5 times 9. So 180 equals whatever a is times 90.
We can divide 90.
Divide both sides by 90. What does a equal? 2. So now I have enough information that I can fill in my equation entirely. I have my a value now. So our whole equation here, our actual factual f of x for this exact polynomial, it's going to have that a value of 2, and then all of our factors, all of our roots. So we're going to have our 2 times our x minus 4, x minus 1, and x plus 3. That is our whole equation in factored form. Is that what we were asked to find? No. We need our standard form, which means we're going to multiply this whole sucker out. So we're going to do this in a couple of sets. We're going to multiply out to standard form. When we're multiplying, it's really important to remember that I can multiply things in whatever order helps. So I can take and multiply these 2 pieces together and these 2 pieces together, and then multiply those. I could also just multiply these 2, and then multiply that times this, and then times this. Whatever works for your brain and what order to do it in is totally fine. I have a tendency to just kind of break it up in chunks like this. So I'm going to multiply the front 2 pieces together, and then I'm going to multiply the back 2 pieces together, and then I'll take those 2 chunks and multiply them. But there's a lot of different orders in which we can do this. So for my left 2 chunks here, I'm taking this 2 times my x minus 4. That's going to give me a 2x minus 8 right here. When we multiply out x minus 1 times x plus 3, that's going to give us x times x gives us x squared. We're going to have a 3x and a minus 1x. So 3 minus 1 is going to give us a 2x plus 2x. If you do it in a couple of steps and then simplify, totally valid. But that's looking at my 2 outside, so that's 3 times x and minus 1 times x. Oops. And then our last term, our constant, would be minus 1 times 3, or just minus 3. Then we get to do round 2. Great. We're going to do another set of multiplication. We're going to multiply the whole thing out. And a lot of times on these ones, it's going to wind up really long, and then we can combine like terms together. If you can combine like terms together as you're multiplying it, more power to you. It is a little confusing sometimes to do it that way. So when we're multiplying it out fully, we should get up our 2x cubed because I'm going to take my 2x times everybody over here. So my 2 times x squared gives me 2x cubed. 2x times 2x give me a plus 4x squared. My 2x times minus 3 gives us a minus 6x. Now I'm going to do all the same thing with my minus 8. Minus 8 times x squared, minus 8 times 2x, and minus 8 times 3. So that's going to give us a minus 8x squared minus 16x plus 24. So multiplying it out and then combining any like terms we have. So our final answer on this one, our f of x, when we combine our like terms together, we should get a 2x cubed minus 4x squared minus 22x plus 24. And this is our equation in standard form. So we went from a straight out list of zeros and 1 point to the whole equation. Questions on this one? I know it's a lot. We're going to do another one like this. So here we're going to be given some zeros. Given is zeros at -1, 0, 2, and 4. And that f of 1/2 equals 63. So again, we're given a point, essentially. We're given an x and a y. So we're going to start by putting it into its factored form with the letter a in place of our leading coefficient so that we could then solve for a. F of x, and we don't know our leading coefficient yet, so we're just going to put our a. What are our factors? X plus 1, x minus 0, or you can just put x either way. X minus 2, and x minus 4. That's kind of our basic-y basic. Don't have to do nothing crazy to it. Factored form, x minus our roots, x minus our zeros. We can find a using our extra tidbit of information. We're going to be able to find a using this guy. Yes, it's fractiony. We can do this. So we know that our f of x is going to equal 63 when x is 1/2. So this side's going to be 63. I don't know my a, but I do know that my x is going to be that 1/2 plus 1. And then we're going to have our 1/2. And I have our 1/2 minus 2. Ooh, wrong color. There we go. And our 1/2 minus 4. There we go. Substituting in that 1/2, and holy cow, did that scale go wild halfway through there. Started very small, wound up very large. So we can simplify these numbers down. Make this be less gross. It's still going to be gross, but that's okay. A lot of times with these, I'll just get these into our improper fractions. So 1/2 plus 1, it's going to give us our 3/2. The 1/2 is just staying as a 1/2. 1/2 minus 2 is going to give us a negative 3/2. And 1/2 minus 4, you can think of it as 1/2 minus 8/2, negative 7/2. We want to simplify this fraction because that's a whole lot. When we are multiplying fractions together, how do we do that? I'm going to get this down to a single fraction. Straight across. So our numerator is going to wind up being 3 times 1 times negative 3 times negative 7. 63.
Why did
Yep.
I say 36?
Because this calculus is totally a thing that can happen.
And it's too early.
It's very early. So we get 63 on the top here. Our denominator, same deal. 2 times 2 times 2 times 2. 16. So if A times 63 over 16 equals 63, what can I do to figure out what A is? Multiply both sides by the reciprocal. I'm going to times by 16 over 63 because that's going to make both the 16 cancel out and the 63 on this side. I've got to move this over just a smidge. I have no space. There we go. But that means I also need to take this side and multiply it by 16 over 63. Because those cancel. And so what is our A going to be? 16. Because those 63s are going to cancel out. So now we have our A value. Now I can take my whole function, I can put in that A, and we can work towards simplifying. So my f of x equals our A of 16. And then all of those factors are going to stay the same. We're going to have our x plus 1 times x minus 2, and x minus 4. And I'm right on the edge of the screen there. And again, we want to multiply this out into our standard form. I'm going to give you guys a second to try that. See what we can get multiplying that out. While you do that, I'm going to pass some stuff back. My pile is getting a little obnoxious. I did also get somebody's 4-1 homework yesterday with no name, and I'm 90% sure it's from somebody in this class because it was stuck between other people from this class. So, double check if you turned in 4-1 yesterday because one of them had no name. Sorry. So when we multiply this out, I'm gonna put all mine up here. I did it in these two chunks. So I got 16x squared plus 16x and x squared minus 6x plus 8. And then multiplying all of those together, we should get 16x to the 4th. And this is not combining my like terms, this is me showing my work. Minus 96x cubed plus 128x squared plus 16x cubed. I'm gonna run out of space. I'm gonna change the view real quick. Minus 96x squared plus 128x. So that's all those pieces fully multiplied out. So when we combine our like terms, we should get our 16x to the 4th minus 80x cubed plus 32x squared plus 128x. And that should be our full standard form equation. There we go, just trying to make sure everything's showing up. There we go, got it all. Just like this. Okay. Questions on these ones? Okay. Tomorrow we'll do 2 more like this, working off of pictures. So when you're working through, I'm 90% sure this is in section 4.3, which we don't gotta worry about timing on that one, so we should be all right. Timing wise, yeah. Okay, so we'll work through 2 more of these tomorrow, but from a picture to write our equations fully in standard form. You guys probably can figure it out, but we're gonna go ahead and do them together tomorrow. And then we'll start looking at our next couple of pieces. Where did I lose you?
Positive 28 and
That would be this 16x squared times this 8. I did my 16x squared times the x squared, 16x squared times minus 6x.
I see what I did.
Okay. I do have for you guys, it is optional, not required, but since I'm not going to see you guys on Thursday, the day before the quiz, I have made for you a review. You do not have to do it, but if you want extra practice on the stuff that's going to be covered on the quiz, it is an option. I'll give points if you do it, but like, I'm not going to count it against you. Okay, I'm going to put those on the table. If you want one, you're welcome to have them. I'm also going to have them tomorrow. If you're going to finish with that, the stack is really thick. I accidentally printed it twice. So, I have many copies. Okay, I accidentally printed it twice. Thank you. Wait. So I have a review for quiz 7 over there, going through the stuff that we need to for the quiz that's on Friday.